Hi, welcome to the Natural Philosophy Symposium 2025. This is a great, unique, exciting event. When Janan Ismail and I arrived here at Johns Hopkins in, Bill, you're sitting up there, a couple of years ago, as new, young, excited faculty members, we thought that this was a wonderful opportunity to do something new, and we thought about what that would be. And we decided on founding what we call the Natural Philosophy Forum. Now, it turns out over dinner last night, we agreed that we do not agree on what natural philosophy is. So I went to Wikipedia, looking up what the ancients believed. They didn't agree on what it was either. So that's okay. It was distinguished at the time, hundreds of years ago, from non-natural philosophy, which was, about theology and souls and what have you. So natural philosophy is exploring the natural world. All of what we now call science used to be within natural philosophy. Since then, the evolution of academia has put people into silos, and you're either a philosopher or a scientist or something else. We want to do our part to unsilo that a little bit. We consider the work of philosophy, certain parts of philosophy and science to be continuous with one another. It's all learning about the natural world using methods of both reason and experiment and collecting data and trying to learn more about it. There is, of course, a bit of a stylistic difference between natural philosophy and much of science. We're a little bit more patient. We're willing to think about the deepest questions at the foundations of our field. In some way, natural philosophy is all about those deep, big questions that got you interested in science or philosophy in the first place. And so we're very excited to have what is at least the first symposium that brings people together, and we brought together an amazing group of people, so we're very excited about that. With that, I'm very happy to have the perfect person to open the Natural Philosophy Symposium, David Chalmers of NYU. I have no idea what anyone's title is, so take it away, David.
Great. Well, thank you so much, Sean and Janan, for organizing this amazing conference with a wonderful group of people. Okay, so since I am speaking first, like everybody, I was kind of wondering what this conference is actually about. What is natural philosophy? So I thought I'd just, have a couple of remarks on this to try and motivate my talk through natural philosophy. I mean, I guess the traditional definition of natural philosophy is something like just the philosophy and science of nature, stemming from a time when there were no separate fields of philosophy and science. People who we would now regard as philosophers, like Aristotle and Descartes, were paradigmatic natural philosophers, as were people we'd now regard as scientists, like Newton and Galileo. I take it that natural philosophy, so understood, is mostly individuated by its domain rather than further commitments. It studies the physical domain, the biological domain, maybe the psychological domain that is sometimes in, sometimes out, but it would exclude things like the supernatural, notably God, not part of natural philosophy, the artificial, and perhaps the cultural. If it's too dependent on the human mind, then maybe it doesn't make it into the traditional version of natural philosophy. Anyway, so understood natural philosophy just individuated by a domain rather than by further commitments. There's also a way of understanding it, though, as a program with commitments. Natural philosophy, alternative definition, can be understood as naturalistic philosophy, which is roughly, philosophy, an approach to philosophical questions that prioritizes scientific methods and rejects the supernatural. The first kind doesn't reject the supernatural, it just says it's outside the domain. Naturalistic philosophy says, there is only the natural, there is not the supernatural. Within the program of naturalistic philosophy, there's something we might call naturalizing philosophy, where we understand natural philosophy now as philosophy that renders its topics as natural, or renders or reveals its topic as natural. To naturalize a topic is to render it or to reveal it as natural, typically relying on scientific methods in so doing. So we can take any of the big spooky topics of philosophy and of science for that matter: consciousness, knowledge, meaning, morality, space and time, free will, and rely on methods of science to render these topics as natural. And I take it naturalizing is at least a big part of the agenda that people have in mind when talking about natural philosophy today. In fact, our fearless leaders at this conference are both major naturalizers. Two of the great naturalizers in today's philosophical scene. Janan writes books like How Physics Makes Us Free, naturalizing free will with the aid of physics. Her book, The Situated Self, does something much like this for the self. Sean's book, The Big Picture, is a giant naturalization of everything. Again, especially in terms of the physical domain. So there's a certain approach to naturalizing which says, naturalizing is basically physicalizing, understanding things wholly in terms of the physical world. And I think much of Janan's and Sean's work takes something like this approach. That's just one version of naturalizing, though. There's another version of naturalizing, which we might call mathematizing. Massaging our topics, trying to understand our topics in mathematical terms, which typically makes them much more open to some kind of natural explanation. I should say physicalizing and mathematizing aren't the only forms of naturalizing. There's also, biologizing, Darwinizing, explaining in light of evolution, computationalizing, explaining in algorithmic terms. And there are many other programs, but these are the two most salient for me today. I asked ChatGPT if it could come up with an illustration of this for me. It did a pretty good job. There's naturalizing by physicalizing. That's one important kind. But the kind I'm most interested in today is naturalizing by mathematizing. And you might think that okay, well, come on, surely physicalizing is the paradigmatic kind of naturalizing in natural philosophy. But then what is a truly paradigmatic work in natural philosophy? Surely it's Newton's Principia. And Newton's Principia is precisely the mathematical principles of natural philosophy. And Newton managed to naturalize many of his topics precisely by mathematizing them. So you can see that mathematizing is approached with very deep roots in natural philosophy. And it's a commonplace that most physical theories are, at least in very large part, mathematical theories cast perhaps largely, perhaps wholly in mathematical terms. Whether it's largely or wholly is going to depend on some things of exactly what we count in the theory. For example, things like the connection to observation part of a theory. Those parts aren't always fully mathematized. On the other hand, you might think, okay, well, sure, eventually we're going to be able to mathematize things like observation and consciousness too. So that's really my topic for today. What are the hopes for a fully mathematical theory of consciousness? This is a program that people have really begun to pursue in the last few years, and I want to kind of step back and look at this program from the point of view of a philosopher. So that was the first section on natural philosophy. I'll also talk in a moment about the program of mathematization, in particular structural realism, mathematical theories of consciousness, some problems for them tied especially to underdetermination, and then an approach I want to advocate, a kind of methodological structural realism about the role of mathematics in approaching consciousness. I should say, in general, I'm pro mathematization. I got started as a mathematician before I switched to philosophy. I'm not always pro physicalization, say in the field of consciousness. I think there are very big obstacles to that, but I'm very attracted by the program of mathematization. So I come to this as at least a sympathizer, perhaps not fully an advocate, but I want to see what can be made to work here. Okay, on mathematization in general, within philosophy, one of the central works here is Rudolf Carnap's Logischer Aufbau, developed the logical structure of the world, where he basically tried to reduce everything in reality to logic and a bit of mathematics. Basically, the Aufbau said we need to cast our theories of the world in purely logical and mathematical terms. Only that will make them fully objective and intersubjectively communicable. It's like for him, logic and mathematics was very special in that it was like somehow standpoint independent and fully objective, and anyone in principle could understand this regardless of their initial epistemic standpoint. Carnap's central motivating example was the railway map of Europe. I live in New York these days, so I thought I'd. Actually, in my last book, I managed to get an illustrator to do a version of this with the New York subway map. You might say, okay, so the initial New York subway map or description thereof is far from just mathematical. It's going to mention specific stations like 8th Street, NYU, and specific lines like the R and the W, and there'll be claims like 8th Street, NYU is on the R line and the W line. But then for you don't actually, for a fully logical or mathematical specification, we can dump the names of the stations and just talk about the first stop on the R line and the second stop on the R line and where the R line and the W diverge and so on. Then you don't need to talk about the L or the R or the W. You can just say there is a line at which the first stop goes like this and the second stop goes like this. And in principle, you can actually get rid of talk of lines and stations altogether and just put it in the form of a graph like this for a fully mathematical description. Now, okay, a fully mathematical description of the New York subway system, like the graph on the right, is certainly going to lose something. It's like, hey, what about the trains and so on? But you might think, well, the structural program is ultimately that's going to be just more structure. We'll fill in, give a fully mathematical account of the trains and the people taking them and so on, and we'll ultimately have a fully structural definition of the word and the world. And the thought is that something similar goes on in, say, physics over time. Maybe initially your physical theories have to use words like English words like mass and energy and charge and time, but actually ultimately you can just give fully mathematical versions of these theories, cashing out words like mass instead as whatever plays a certain structural role, and give a fully mathematical account of physical reality. That, at least something like that, was Carnap's program in the Aufbau and is the program of structural realism. So this is just the process of moving from a sentence in a more than mathematical language, structuralizing all the key terms, and ending up with a key claim about the world, like there exist certain things, there exist certain entities. In the case of the subway station, there exist certain entities and there exist certain relations, so that these entities are related in such and such a way according to these relations, and that can just all be put as roughly a quantified sentence in a purely logical or mathematical vocabulary. Structural realism, say about physics, says basically that's how we can understand what physical theories ultimately say about the world. I mean, there are many forms of structural realism, but one very informal way to put it is that, physical theories are in the business of characterizing the mathematical structure of the world and can be put fully in those terms. There's the ontic version that says that's all there is to reality. The epistemic version that says that's all we can know about reality. But here I'm just understanding it as a claim about what physical theories say, when that's at their core, where that's, I think, something like this is a widely held view. Carnap argued for a much stronger thesis. All truths about reality can be captured in structural and mathematical terms. You might say, well, yeah, even consciousness. Well, actually, about half of the Aufbau, or a very large portion of it, is trying to give a mathematical/logical characterization of consciousness in terms of one basic relation, a relation of phenomenal similarity, which he used to define up things like qualia, and ultimately got rid of the relation R to yield a purely logical mathematical description. So the Aufbau itself gives a structural model of the qualities, not just of physics, but especially of consciousness. And this is a program, I mean, it's widely held that this was unsuccessful, but this is a program which is now coming back in this whole idea of mathematical theories of consciousness. So let me just say something about consciousness. Whenever I say consciousness, that term is interchangeable with, is to be understood as what philosophers call phenomenal consciousness, which is roughly equivalent to subjective experience. Whenever you hear the word phenomenal or phenomenology here, for me, that's a philosopher's shorthand for talking about subjective experience. States of subjective experience are roughly states such that there's something it's like for the subject to be in them. You all know Thomas Nagel's famous paper, "What is it like to be a bat?" And the thought is, as long as there's anything it's like to be a bat, then the bat is phenomenally conscious. Phenomenal consciousness is not to be understood in terms of intelligence, in terms of access, in terms of self-models. I mean, those things may turn out to have some very deep connection to consciousness, but that's not our initial subject matter. There was a nice little, I was at the TED conference a few weeks ago where Claudia gave a talk, and there was a nice slide on this there in an interview with Sam Altman, where consciousness versus intelligence came up, and they put one of the OpenAI models to work on illustrating it. And here we have consciousness feels like something versus intelligence figures stuff out. And yeah, our subject matter here is very much the feels like something brigade. Although there's a little ideology here that makes it look like the biological system is more apt for consciousness and the silicon one more apt for intelligence. Well, all that is that's grist for Anil's mill. Maybe we'll hear more about that later on in the conference. But our consciousness breaks down into many different components: sensory experience, affective experience. Sensory experience, like the experience of seeing, hearing, sensing one's body. Affective experience, like the experience of pleasure and pain, and emotion. Cognitive experience of thinking and reasoning, maybe more, but that's going to be enough for now. Now, psychology, as we understand it, was founded really in the mid-19th century as not just a science of the mind, but as a science of consciousness, and in particular as a mathematical science of consciousness. The psychophysics that people like Weber and Fechner got going in the 19th century was all about mathematical principles connecting things like properties of the stimulus to properties of a conscious experience. And you have all of these well-known laws like the Weber's law and Fechner's law, which give mathematical characterizations of the felt intensity of a sensation based on objective properties of the stimulus. Later on, we've got Stevens' power law that tries to do the same thing in different frameworks. And psychophysics, today is still very, 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 very mathematical and can be construed as at least one potential building block for a mathematical theory of consciousness. Now, traditional psychophysics, at least, is pretty low dimensional for one or a few dimensions of consciousness at one time, like the felt intensity of a certain sensation, or the experience of brightness, and so on. Of course, consciousness is actually extremely high dimensional. It consists of experiences, very high dimensional experiences in many modalities all at once, many interrelations between them. So it's a good question to ask: can there in fact be a complete mathematical specification and a complete mathematical theory of consciousness, including all of its aspects? There is now this program of mathematical consciousness science has gotten active enough. There's now actually an association for mathematical consciousness science that holds a meeting every year or so that explores many different approaches to understanding consciousness mathematically. I won't have time to go into much at all of the specific work, but just thinking about theories of consciousness more generally. I mean, a theory of consciousness will involve a number of components. We need some way to actually be able to specify states of consciousness in some reasonably rigorous way. We need to be able to map states of consciousness, conscious experiences to things we already know about, in particular in our model of the physical world. So there's a program of finding physical correlates of consciousness. Most well known is the program of finding neural correlates of consciousness, the so-called NCC. Finding some reasonably rigorous way of systematizing the connection between consciousness and the brain in the first instance, but physical processes more generally. Ultimately, we want some kind of psychophysical principles that connect physical states to states of consciousness. When you have such and such physical properties instantiated, you have such and such states of consciousness instantiated. All this is actually consistent with different views on, say, the philosophical mind-body problem, materialism, dualism, and so on. That will come down to how strong, how tight these, the metaphysical status of these principles. But this is just a very generic setup for a theory of consciousness. A mathematical theory of consciousness then will just involve making all these components mathematical. We'll have a mathematical specification of conscious states, called this mathematical phenomenology, a mathematical specification of the physical correlates of consciousness. I think one dream here is what we might call the MCC, not the Marylebone Cricket Club, but the mathematical correlates of consciousness, which is some kind of mathematically specifiable property such that consciousness arises wherever that property is to be found, and indeed mathematically specified psychophysical laws. Now you might think, okay, this is a big ask. Do we actually have anything even a little bit like this? I mean, there is this interesting example of a theory which is out there, the somewhat notorious integrated information theory put forward by Giulio Tononi and his colleagues, which does, this is an extremely controversial theory. Some people call it pseudoscience, mainly because there's not very much evidence for it. Its status is kind of a little bit like the status of, if you pick your least favorite theory here. The way some people talk about string theory, but worse. Like mathematically cute, but very difficult to falsify, and right now not much evidence. But what integrated information theory does, it's got some nice math of the certain underlying network systems specified as basically Markov-like networks with probabilistic translations between them, and it defines a certain property in terms of that which it calls phi, and you're supposed to get consciousness whenever phi is greater than 0. It also defines a more fine-grained mathematical object which it calls a phi structure. That's what you have there under conceptual structure, which it claims gives a specification of a full-scale conscious experience, not just a quantity of consciousness, one-dimensional, but a very much multi-dimensional mathematical object, which it calls a phi structure. So, its mathematical specification of conscious states is done in terms of this phi structure. There's a mathematical correlate of consciousness. This mathematical correlate of the presence of consciousness, or being conscious, is just the unidimensional quantity phi, having phi greater than 0. And then there'll be a mathematical psychophysics, which I'll get back to the details of that in a moment. Like I say, I don't find the IIT especially plausible myself. I think the evidence for it is weak, but it is a very nice example of the kinds of thing that might make we would want a mathematical theory of consciousness to do. And abstracting away from the question of whether there's any reason to believe it, I think it provides a nice example of the structure to analyze. And we can use this to address certain potential obstacles to the program of mathematizing consciousness. Here there's basically one major question is a question of completeness. Can a mathematical theory be a complete theory of consciousness? And here this kind of roughly corresponds to the project of ontic structural realism in, say, the physical case, where the certain mathematical or structural descriptions are taken to be complete descriptions of physical reality. Could we give a complete description of mathematics in mathematical terms? And here there are some fairly predictable reasons for saying no, at least predictable if you know the existing debate about whether consciousness can be understood in physical terms. Some of the same issues come up for mathematics. Can there be a complete mathematical specification of states of consciousness, or does mathematics always underdetermine phenomenology? I mean, Nelson Goodman, in his book, The Structure of Appearance, provided a very lengthy critique of Carnap's mathematical construction of conscious experience, basically saying that the mathematics always underdetermines the phenomenology there. Does that apply to every mathematical characterization of consciousness? And here's just some very simple example of mathematizing one aspect of consciousness in a very naive way. Let's just take an ultra naive model of the visual field, but we treat it kind of like a giant TV set. It's a square which can take on a three-dimensional value, like a color value, at every point within the square. Maybe we can model this. Let A be the interval from -1 to 1. Spatial locations will be two-dimensional quantities in A squared. You take two of those, two values in A, you get a location. A color is a three-dimensional value in A cubed. A field to be composed of a color in A cubed for each spatial location in A squared. And so a whole visual experience will be specified by a function from A squared to A cubed. Intuitively, a location, a color for every location, but we don't need to use words like color and location here. We just do it with the math. I mean, this is oversimplified in so many ways and just plain wrong in so many ways. But the thought is all the ways, or at least many of the ways in which it's wrong, are precisely matters of mathematical structure. Yeah, to get this right, you're going to need the geometry to be like this, and you're going to need some attention structure, and you're going to need a better model of color space. But all that is just more math. So, you can see this is motivating the principle of mathematizing phenomenology. But anyway, so the worry is that kind of mathematical characterization will always underdetermine phenomenology. And there's at least three versions of this worry. I think I'll skip over Newman's problem given time, but I'll first talk about structural quality gaps and then about this Rosetta Stone problem. I mean, one basic worry is that all that math will underdetermine the phenomenology. Nothing there will actually tell you, what, for example, it's like to have an experience of red. I mean, one minimal worry is that specifying a function like this doesn't even tell you that these properties are phenomenal properties, that they're subjectively experienced. It could just be a TV set out there in the world, so to speak. So at the very least, we need some way to specify that these are phenomenal dimensions. I'm happy enough to take such a notion as primitive and allow a little bit of non-mathematics in our specification, saying, oh, these are dimensions of subjective experience. Other people might try and cash out phenomenology in some terms of its structural functional role. More specifically, it might say it doesn't entail that some dimensions are color and others are spatial, just saying it's a three-dimensional value. There's all kinds of three-dimensional values that aren't colors. I mean, the structuralist program would be to try and capture the distinction, say, between color and space and so on in terms of some underlying further structure, the distinctive roles played by color. I'm a little dubious this can work, but it's at least a strategy. There's the familiar kind of worry you get from thinking about, does anything about the specific phenomenal qualities, say, of experiencing color, the experience of yellow and red, fully captured by this kind of structural description? Maybe we could invert all of our sensory experiences of colors, swapping yellow and blue or red and green, and so on, in so-called inverted spectra, and therefore structure will underdetermine qualities this way. There, a natural response is to try and invoke more structure to draw those differences, although it turns out to be extremely hard to actually make that work. There's a more general worry for mathematical approaches here, which is a kind of generalization of the famous thought experiment of Mary in the black and white room, who's never experienced, she's a color scientist, but she's never actually experienced colors other than black, white, and shades of gray. you could make the case that for any mathematical specification, well, of anything, but in particular of experience, Mary could know all those mathematical facts. Mathematical facts are by their nature objective, open to anyone from any epistemic standpoint. Mary can know any purely mathematical facts about the experience of red. She still won't know what it's like to see red. Therefore, there'll be a gap from any kind of structural description to redness. Now, here there are various familiar responses from the debate about physicalist approaches. You might say more mathematical structure will close the gap. You might say these apparent further qualities are an illusion. You might say the gap is epistemological, not ontological. I'm not going to go into that long dialectic here. My own view, though, is that structural quality gaps suggest that any purely mathematical or structural specification of a conscious state underdetermines that state. And if so, no mathematical theory of consciousness will be complete. That said, so this suggests to me that ontic structural realism, at least, about consciousness is false. Other versions are still on the table, and in the tiny amount of time I have left, let me just say something about what I call methodological structural realism, which is something like, finding mathematical theory of consciousness can still play a crucial methodological role in theories of consciousness. Our theories of consciousness ought to characterize the mathematical structure of consciousness and the mathematical principles governing it. Even if mathematical specifications are incomplete, they should be at the core of the science of consciousness. They kind of provide an objective skeleton for the specification of conscious states, which will always be somewhat incomplete because of this, missing acquaintance with phenomenology, but can nonetheless play crucial roles. Why? Structural properties are fully intersubjectively communicable where non-structural properties are not. And this is a point that both Tom Nagel and my recent PhD student Andrew Lee in recent work has put forward in work on structure as a kind of objective phenomenology for characterizing experiences, yielding properties which can be studied with formal and contrastive methods, and which link very well to potential mathematical or structural physical correlates of consciousness. So I think there really is an interesting project of mathematical phenomenology that aims for a correct and complete characterization of phenomenal structure. It doesn't characterize the non-structural aspects of experience, but let's at least characterize the structure as well as we can. And then there's a question of what kind of mathematical object is best suited for that. You can try and specify psychophysical laws in a certain mathematical form. Maybe I'll skip over this general form and how it comes out in IIT. But I do want to raise this Rosetta Stone issue, which, if you look at, say, integrated information theory, it gives us this mathematical object listed here under conceptual structure, and that's meant as a specification of a state of consciousness. Now, my attitude when I first saw these things is like, okay, great, it's an interesting mathematical object. Now, what on earth is that thing actually saying about consciousness? I felt like I needed a Rosetta Stone for the theory to take this phi structure and turn it into a claim about consciousness. And maybe Tononi and other researchers have some idea of how they want to turn that mathematics into phenomenology, but somehow that Rosetta Stone needs to be made available to the rest of us. So in order for any mathematical specification M to tell us something about a state of consciousness C, we need to translate that mathematics into phenomenology, a Rosetta Stone for interpreting mathematical descriptions as phenomenological descriptions. And I don't think we really have that for IIT yet. I don't want to say it's impossible. Other specifications, the kinds you get in psychophysics, maybe the Rosetta Stone problem is a lot easier. This connects to the famous Newman problem, but which also turns to some degree of underdetermination by fully mathematical descriptions. Both of these problems suggest you actually need some extra mathematical vocabulary to interpret the mathematics as saying something about phenomenology. And there's a really interesting question: what kind of extra mathematical vocabulary should be added to our mathematical phenomenology to give a fully adequate structural specification of phenomenal states? Here I'm not talking about getting to the redness and the greenness all over again, just to understanding phenomenal structure. This could still be a broadly structural vocabulary accessible to arbitrary competent thinkers. And here are some candidates for what that maybe a mereological vocabulary. These are the parts, these are the wholes, these are locations, these are the qualities. Here's some representational structure, just some candidates for what might go into that Rosetta Stone program. Anyway, I think there's a project here of mathematical phenomenology, which can't be purely mathematical. It's going to have to involve developing and analyzing key structural concepts for translating mathematics into phenomenology. But I do think this is actually a viable project. So to conclude, there's a famous line by the philosopher Saul Kripke, there's no mathematical substitute for philosophy. And I was tempted to say, okay, well, there's no mathematical, this kind of analysis might suggest there's no mathematical substitute for phenomenology either. I think that's not quite right. There's no complete mathematical substitute for phenomenology, but mathematics plus some extra components may get us all the way to phenomenology. And that said, mathematical theories may well be kind of at the core of the project of having an objective theory of subjective experience, complete or not. I think, methodologically will do very well to put a mathematical approach to consciousness at the center of the science of consciousness. Thank you.
Thank you very much, John and Janan, for the invitation. I'm also very excited to hear the other talks by the other speakers here, so it's great to get to come. I should start out by saying I really didn't have that great of an idea of what a commentator was supposed to do, so I'm more or less just taking it as an excuse to say things I find interesting, and maybe Janan and Sean will tell me I did it all wrong later, but we'll see. I should also say that I only have partially philosophy background, so I'll probably be much more philosophically sloppy than David was, so temper your expectations a bit on that to start. But what I wanted to do is just try to pick up, for the most part, on the underdetermination issues that David raised, and so a couple of talk applied modeling as a resource for addressing underdetermination. And so I'm coming at this from more of a practitioner's angle. So my lab, I'm at a brain research institute, focuses on a field called computational psychiatry. So basically what we do is we fit mathematical models or computational models of cognitive and neural processes to perception and choice behavior, mainly in people with psychiatric disorders. And so we try to use those models to identify kind of mechanisms of the abnormal phenomenological experiences that people have. So I'm hoping that this might provide a kind of more complementary perspective on mathematical models of the mind and maybe highlight some other resources that are kind of naturalism friendly. So a couple of preliminary points. One, I kind of wanted to say that in one sense, in kind of a practitioner's perspective here, underdetermination problems, like what David mentioned, do seem right. Modelers in cognitive science confront this pretty regularly, where we have the mathematical structure, but then we have to kind of decide what psychological labels we want to put onto the math. And sometimes you'll find that models can just be labeled a different way. It can be the same kind of model and still used to model different phenomena. But at the same time, these models in cognitive science have been fairly successful at reproducing empirical patterns in perception and choice behavior. And crucially, that includes accounting for brain activity and behavior during conscious versus unconscious perception. So I think we do want some kind of a clear account of how and why these models can be increasingly successful. Another kind of preliminary point I wanted to make was that many mathematical models implicitly presuppose some type of functionalism, which just means that the psychological content of an internal state depends on the computational role that it plays in the system. So in other words, it doesn't have to be implemented by kind of ions and lipids bouncing around in the brain. Silicon or whatever can do the trick so long as it's kind of fulfilling the same computational roles right down to the lipids and proteins bouncing around inside cells. And so I think as a result, these models inherit a lot of the same explanatory strengths and weaknesses of functionalism generally. And here's where I think concrete applications might offer some useful insights, both in providing ways of thinking about addressing underdetermination problems, as well as offering utility for conducting kind of more precise thought experiments in philosophy, where they can actually take advantage of simulations and things like that, very quantitative. So what does an applied mathematical model look like? And here I'll give an example of a concrete Bayesian brain model of consciousness. And this is work that was done in collaboration with Jakob Howie and Christopher White, who's a grad student that I co-mentored previously. And just to kind of embarrass him a little in case he watches the YouTube of this later, he's a very impressive graduate student, so look for him. He's going places. And so the task that we wanted to model was based on a study by Pitts et al. In 2014. And basically the way that it works is you have people staring at these black discs on the outside, and they change colors quickly between black and red. And every time they change, the person is supposed to press the button as quick as possible. At the same time, there's these moving lines in the center. But they're not relevant to the task. And so when people's attention is very kind of highly focused on this, occasionally a square will appear, and then it will go away. And so we asked the person, did they see the square? Now, because this is a Bayesian model, we had to get Thomas Bayes in here, so we'll just call our participant Tom. And so we asked Tom, did you see the square? And then a lot of times participants will say they didn't see anything. And so despite this, if you're measuring brain activity, like with EEG, for example, you can get these nice distinctions where when the response to the square was seen, you get this nice kind of P3 response, whereas when it's not seen, then you can see that that second part of the response is absent, even though the first part is still present. And so what Chris did is he applied this mathematical hierarchical Bayesian model that I can't go into at all. But basically, you describe a task in terms of a graph, and then there's fancy iterative update equations that describe the dynamics, and then there's a mapping that's proposed between that and the way that you can simulate neural responses in the brain. And so the graphical model of this specific task works like this, where you have the inputs, where the task stimuli, so in this case, squares versus lines, red versus black stimuli, and then you have the words that Tom can choose to say. And then you have the level 1 states, and those are just representing simple perceptual representations. And then you have this second level that's more integrative, where basically the perceptual representations are integrated together and inform goal state selection that's motivated by this expected reward for accuracy, which then translates back down into the word selection based on the goal. So just to kind of briefly convince you that these are useful models, you can kind of simulate neural responses here, and you can see that when attention is present in the model, Tom sees a square. He reports it like 99% of the time. And in the neural simulations, you can see that the response more or less matches the broad kind of character of the empirically observed ERPs. And then when attention is absent, you see much weaker neural responses. Tom only reports seeing it about 36% of the time in the model. And the simulated ERP response also matches the empirical response. Only the early response is present. And this generalizes to other tasks. With report versus no report paradigms, it can reproduce patterns of neural responses that have been observed. And it can even make novel predictions. In this case, effects of expectation, which were subsequently confirmed in a study in this specific case, which Chris was, I know, excited about. But the whole point of showing you this is that you can kind of see pretty quickly where an underdetermination problem arises. So by itself, it's not really clear what determines the content of the mathematical structure here. But in practice, right, it's the causal connections with the environment that provide the resources for determining that content. So for instance, as soon as the inputs are actually, right, squares and lines and red and black circles from the environment, then we can kind of infer our way back, right, into what the content of the math is supposed to be. And that also, the structure also allows for interesting thought experiments. So for example, what if we think about more complex stimuli? Like what if I replace this with, say, spiders and bunnies, right? And we infer our way back to spiders and bunnies all the way up. Now, those are much more complicated stimuli. They have affective qualities associated with them. So we can think about, what has to change in the model structure, like in the likelihood functions, to make that structure work about bunnies versus circles. And, does that have any generalizable lessons? Another thought experiment that is just something that I like personally, actually wrote one of my first philosophy papers about it like 10 years ago, right at the end of grad school, is this evil neurosurgeon thought experiment. So where you can kind of swap the connections, right? So if I just swap just those, right, keep everything else the same, and replace them with a different set of synaptic connections, then there's interesting things that happen. So the first level states will still detect squares accurately, right? But now Tom's going to report experiencing a square whenever it's absent, right? So we can ask, do we believe Tom or not in this case, right? If we do believe him, so we say, oh, he's just hallucinating squares, then we kind of have to say that the phenomenology here, the phenomenological character depends on how the perceptual states are guiding goal selection, right? So it's kind of like what the first level tells the second level, even if the first level is still actually detecting and representing something else. If we don't believe him, instead, we say he's really not experiencing squares because it's the content of the first level. Even if he insists he's not, then kind of seems like we have to reject the reliability of self-reported experience, and that could kind of threaten the falsifiability of or that's possible worry of a theory for a theory. And so I hope this just shows that there's some utility applied that can come from applying specific kind of concrete models as opposed to just thinking of them abstractly. Generally, they kind of highlight how having a body in an environment with real inputs and outputs could play a role in sort of figuring out what the content might be. And that parallels the sort of stress placed on inputs and outputs within standard functionalism generally in philosophy, and also echoes theory stressing the importance of embodiment. And like I said, it allows these quantitative thought experiments, and in this case, suggests conscious content. Part of that might depend in interesting ways on specifically how perceptual states guide goal selection. And if people are interested in the evil neurosurgeon example, this is that paper from like 10 years ago. Like I said, it's just one that was close to my heart. But I did want to highlight at the end here that embodiment does have its challenges. So for instance, is a brain in a vat conscious? If we can mimic the right inputs and outputs to a brain, and that's sufficient for experience, it seems like the real inputs and outputs are unnecessary. And it does kind of seem like a Bayesian brain in a vat would be conscious. I mean, it needs to infer the external states causing sensory input anyway. And, of course, we could build, right, that circular input-output structure, like from the matrix or whatever, into a mathematical model as well. But now we're just back to only having abstract mathematical structure. And so I think the underdetermination problem returns. Again, this kind of parallels classic challenges to functionalism. So just summing up, the main point I wanted to make is that considering concrete applications of mathematical models does seem like it can be instructive in offering additional resources when thinking about approaches for mapping the math to mental states. But regardless, I think some of the pesky problems still arise, so it's not a clear solution. So with that, I just want to say thanks to Chris and Jakob and acknowledge my lab and the institute where I work. Also, big thanks again to Janan and Sean for organizing this and for the invitation. And thanks for listening to my ramblings.